next week, and we'll do some labs beforehand that cover these things so we can hopefully clear up questions about them and all that stuff. And hopefully the Canvas quiz this week helps clear up some of that stuff too. All right, so the first section is 2-3. We'll be talking about functions. This is by far the longest section of the night. The rest of the other two are not nearly as long as this one is. This one has a lot of stuff in it, but it's easy stuff, I think. So, or some of it's pretty easy. Some of it's not as easy, but it's not hard. All right, so functions. Functions are based on relations in math, and relations are sets of ordered pairs. Okay, ordered pairs being like x comma y in parentheses. So x and y values usually depict those as sets of ordered pairs. Ordered pairs written in that direction, x comma y. All right. So a relation would be a set of ordered pairs like something like 1 comma 2, x value of 1, y value of 2, 3, 4, 5, 6. So, just any set of ordered pairs is considered a relation. In a relation, you have a thing called a domain. The domain, the x values. Okay. So if we look at that relation that we've got here as an example, the domain of that would be 1, 3, and 5. And you put that as a set, 1, 3, and 5. The range of a relation deals with the y values. That would be the set of the y values from those ordered pairs. In this case, 2, 4, and 6. And curly braces around those to depict sets out of that. So a set of ordered pairs is a relation. The domain of a relation are the x values that go with it. The range of the relation, the y values that go with it. Now, the title of the section is functions. So a function, by definition, is a relation in which one value from the domain corresponds to one value from the range. Okay? Now, layman's terms, easier way to remember that is if it's a function in the relation, when you're looking at a relation to determine if it's a function, don't repeat x values. Okay? Don't repeat x's. Right? All right, don't repeat your x values. Okay, it's kind of like I tell my high school students this because they're all like starting to date and stuff in high school, and I tell them if they want to function properly, don't repeat your x's, and they find that funny and life altering for some of them. But if you want to function properly, don't repeat your x's. That kind of is a good way to remember that. So if you're going to be a function, don't repeat your x values in this case. Okay, so no repeating of x values. It's okay to repeat y values. Okay, maybe that's a side note that you need to make. We'll use a big word, permissible, to repeat y values. But you cannot repeat x values and be a function by definition. Okay, all right, so let's look at some examples and we'll play the game. Is this a function? Why or why not? Of course, you have to have an explanation. a simple yes or no would not do. We need to know why or why not. So let's start with a set, or just a relation with some ordered pairs. 1, -6, 3, 5, -2, 4, 7, -13. Nice relation there. Set of ordered pairs, got 4 ordered pairs in there. Question is that a function? Why or why not? Well, what's the only rule we have to worry about? Don't repeat the x's. Are the x's repeated? No, we got 1, 3, -2, and 7. No repeat of x's, so this is yes. There are no repeated x values. So yes, it is a function. There are no repeated x values in there is what makes that legal. Okay? All right. That's easy. They won't always put functions or relations in set notation like that. A lot of times they'll put them in a table like we just saw in a lab there. That's a very common way of writing a relation in a table with x and y values, like 4, -8, 3, -2, 6, -5. All right. So 4, -8, 3, -2, 6, -5. Is that a function?
Yes.
Okay. No repeated x values. All right. So even in the table format doesn't change it any. Scroll up, we can still see that. Everybody writes as fast as what I'm thinking. All right. So sometimes that table can be written sideways, like this. This is a lot of textbooks do it this way. I really don't like sideways ordered pair tables. It seems more logical to put them vertically. I don't know. Maybe that's just my OCD kicking in, but it doesn't matter. -5, 7, 8, -2, -5, 9, and 10, -1. See, to me, that just looks like 5,800 or 58,510. That's why I don't like it anyway. But it's the 5, -5, 7, 8, -2, -5, 9, 10, -1. Is that a function?
No.
Why not? Yeah. X value -5 repeats. That would be what fails that. Okay. So tables, pretty common way of doing it. A little less common way would be what's called a mapping, is what this is called. So if you see this, it's called a mapping. It's just bubbles. Got a bubble that's the domain, and you got a bubble that's the range. So it's just another way of arranging those things. And they'll put some numbers in the domain bubble, like 4, 6, 7, and -3. And then they might put 100, 200, 300 in there, and they map the domain values to the range values. And by mapping them, I mean they just draw arrows. It sounds like it's a big fancy thing, but it's just arrows. And then what it does is it creates out ordered pairs. The arrow 4, 200 is an ordered pair. 6, 100 is an ordered pair. 7, 300 is an ordered pair. And -3, 200 is an ordered pair. So is that a function? Yes. What's repeated here? 200, the y value, the range value of 200. So yes, no repeated x's. So you can see, it's the same reason there the whole time. Very easy to catch one that is not a function out of that, in that style. They got the domain and the range bubbles. Very easy to catch one that messes up 3, -8, 10, -6, 2, -5, 7. And when they do these mappings, they might have 3 going to 2, -8 to 7, 10 to -5, and then 6 to 2, but then they may have 3 going to 7 as well. So it gets a little jumbled with the arrows, but the big thing to look at is what? Yeah, those 2 arrows coming out of a 3, coming out of a domain bubble. So that makes it real easy to say this is no x value 3 repeats. The reason behind that. Okay. So those are, if you've got ordered pairs, the different ways the ordered pairs can be represented as a set, as a table, as a mapping. Always a good way to represent ordered pairs. Ordered pairs can also be represented in graphs, and we're just going to sketch some graphs. Not going to really graph them on a coordinate plane or on a grid, a nice grid. I'm just going to be kind of generic with my drawings, but I'm just going to graph some stuff, and we're going to determine if it's a function or not. So coordinate plane here, x and y axis, and then maybe this blue thing. That's our relation. That blue line represents all the ordered pairs that fit there. And there's an infinite number of them. We couldn't check every single x value, every single y value, because there's always more of them, right? Because that line keeps going in both directions. So the way to do that is with what's called the vertical line test. You may remember this. You may not. It's not very difficult. The way the vertical line test works is you take a vertical line and you try to place it anywhere on the graph. You actually got to try to think everywhere on the graph. But you're looking for a place that if I place that vertical line on the graph, it hits it more than once. That's what would make it fail it. Because that implies that there's an x value repeating if it touches it more than once. No matter where I put a vertical line on this particular graph, if I put one there, it only hits it once. If I put it over here, it only hits it once. If I put it down, right there, it only hits the blue line one time. No matter where I draw it, it's hitting the blue line only one place every time I draw it. That passes the vertical line test. So this is a function. Yes. Passes the vertical line test. And we'll call it VLT. That means there's no repeated x's. If it passes the VLT, that means it doesn't have any repeated x values. Vertical line test. Okay? Anytime you've got a graph thrown at you, that's the way to test it. Because you can't get all the ordered pairs that are there. You can only test the actual picture of the graph. All right? Let's look at another graph. Coordinate plane. I didn't do that very well. Oh, that's much better. Okay. Kind of a weird looking shape. There's an equation that goes with that. You don't need to know it for this class, but either way, that blue line represents a bunch of ordered pairs. That's all that blue line represents. Anytime we do a graph, that's what it represents, a bunch of ordered pairs. Then the question would be, okay, is there anywhere I can put that would fail the vertical line test? Well, if I put my vertical line right there, it touches it twice. I can put my vertical line way back here at the back, and it only touches once. It passes in that spot. But if I move anywhere else, it's going to touch it twice, right? So that would fail the vertical line test. It only takes one point of failure. And so here it hits twice on a vertical line. So that fails the vertical line test. So this is not a function. Fails vertical line test. That means that these two spots right here have the same x value. I got a different y value, but that's the same x value. And that's a no-no. Can't have that.
Question. I've got to leave. Is this being recorded?
Yeah, I'll post a link on Canvas. Yes, sir. Yes, sir. All right. So vertical line test, anytime we got a graph, that's how we want to test, see if it's a function or not. Okay. All right. Let's look at kind of take that graph and build off of it. Coordinate plane. Almost the same picture, just turned. Does this pass the vertical line test or fail it? It would pass it, right? Because no matter where I drop that vertical line, it's only hitting it in one spot every place there. So this is a function. Passes the vertical line test. I don't know why I didn't abbreviate that there. Let's fix that. The BLT. All right. One more, and then we'll move on to the next thing. Coordinate plane. It's kind of football season. We'll use the mathematical equivalent of a football. An ellipse. That's what that shape's called. Squish circle. Is that a function? Easily not. Fails the vertical line test. Easy stuff right there, right? Okay, now, when we're talking about functions, we've looked at tables, we've looked at sets, we've looked at mappings, we've looked at graphs. The only other way a function can be expressed would be an equation. So that's where we're headed next, is equations, functions as equations. And when we talk about functions as equations, we want to talk about their domains. So domain of functions in equation form. If they're in set form, it's just a list of the x values. If they're in table form, it's a list of the x values. If they're in a mapping, it's just that bubble that says domain. That's really easy then. Okay, if it's a graph, we can look at what x values does it cover. We'd have to have more specifics about our graphs if we were going to do that. But if we're looking at an equation, there's some things that we've got to look for. And what we've got to look for are these red flags. There are only two red flags that you have to worry about when you're looking about domain of a function in equation form. The first red flag that you have to look for is x's or variables. X is the one we're looking for in the denominator. What do I mean by denominator? I mean the bottom of a fraction. If there's a variable in the denominator, the bottom part of a fraction, that's a red flag, and we're going to learn what to do with that. Okay, so that's one of the red flags we're looking for. The other red flag that we're looking for is an x on the inside of a square root. And as you get into 110, we'll say even root. But square roots is what we deal with in this course. Square roots is all you got to worry about. Even root, that'll be something we'll talk about when we get into 110. Okay? Those are the only two red flags that you got to look for. You're looking for x's in the bottom of a fraction or x's on the inside of a square root. If you see those things, you got to do something about the domain. Otherwise, the default for domain, if there are no red flags, no red flags. And the domain is all real numbers. And we'll write it like this in a set notation. That's a x, then a straight up and down bar, and then the words all real numbers, all in the curly braces. That's set notation. Okay? X, as long as X is a real number. That's what that says. And that's how, mathematically, it just means X is a real number. Okay? And then there's a thing called interval notation that we're going to deal with. Negative infinity to positive infinity. That's these two mean the exact same thing. All real numbers, negative infinity to positive infinity. That means as far as you go in the negative number world, positive infinity means as far as you can go in the positive number world. Okay? Negative infinity to positive infinity is how that's read. Okay? We're going to do both of these as we go through the set notation and the interval notation. You got to learn. Interval notation may be something that's foreign to some of you. You may not have seen it before. Set notation, you probably have seen that before. Maybe not have used it a bunch, but it's more common than the interval notation as far as especially high school math goes. The interval notation is making a good comeback in high school math, though, which I'm glad of because I like it better because that's what I'm used to. All right, so the default domain, all real numbers. That's the one you would normally pick, okay? Unless there's red flags. If there's red flags, you know you got to change it, okay? That's when you got to change your domain, is when there's red flags. So we're going to look at some equations and get the domain looking for red flags. If there are no red flags, what's the domain? All real numbers, negative infinity to positive infinity. That's the interval notation for that, okay? So let's look at some examples, and then we're going to figure out what to do, okay? What letter are we on? J. Example J. We want to find / state the domain. Okay? All right. Let's start with an easy one. Y equals X plus 4. Okay? Now, we look at that problem. What are we looking for? We're looking for domain. What kind of things help us find a domain? X's. So we're looking at X. We're looking for X to be where? For something to change what the domain is, where would X have to be? What's the red flags? That's what I'm asking. All right, so can't be in the denominator of a fraction. There's not even a fraction in the problem, right? So that red flag's out. Is there a square root in the problem? No, neither of those things exist. So that means that this one has no red flags, meaning that the domain would be all real numbers. X such that X is all real numbers. That's the set notation. The interval notation, we're going to do both because there's applications of both, and this textbook tends to bounce back and forth. So as you're doing Canvas quiz and test in here, it uses both set and interval notation. So we got to use both. All right. The interval notation for all real numbers is from negative infinity to positive infinity. That's the X's. X's fit that interval from negative infinity to positive infinity. Because there were no red flags in this problem. That's why the domain is that. Okay? Now, look at example K. Y equals 5 over X plus 2. Oh, there's a fraction. And what in the bottom? X. That's a red flag. Okay? So that's a big deal. Now, here's what we've got to get out of that. What's the only number that you cannot divide by? 0. So we've got to find what would make the bottom of that fraction 0. That's what we have to find. And the way to do that is just take the denominator and set it equal to 0 and solve that equation. Whatever the denominator is, it's got the variable in it. Take it, set it equal to 0, and solve it. That's going to find you when the denominator will be 0, when you're dividing by 0. So, subtract 2 Use a different color. That'd be -2. That's the only number that x cannot be. Okay? So our domain works like this. Set notation. X, as long as x is not -2. The set notation for that is super easy. Okay? Now, the interval notation for that is a little bit different, a little bit more difficult, but it's important that we learn it. Okay? Now, what we're doing when we have an exception like this is we're taking the negative infinity to positive infinity and we're cutting a number out. We're saying, okay, we're going to start at negative infinity, which if you think about a number line, let's pretend that this door is negative infinity and that door over there is positive infinity. Okay? I'm x. Okay? I'm walking along, I'm going pretty good, and then this plug-in right here. That's the problem. That's the -2. I can't use the -2. So what I've got to do when I'm walking along that number line from negative infinity, trying to get to positive infinity, I've got to hop over that problem. I've got to skip the -2. All right? So I'm going to cut out a -2. So when I go to that, I'm starting at negative infinity. I'm walking along just fine until I get to -2. And I got to skip it. So the way you skip it in interval notation is you say, okay, from negative infinity to the number I want to skip. And then I use a parenthesis and say, at -2, I got to jump. And I got to land right after -2. And then start walking again. So it's like I'm walking along from negative infinity. I'm walking just fine. And then I'm coming up to -2. And I've got to jump over it and land right beside it. And then start walking again. This is the notation for jumping over it. It's called a union. Negative infinity to -2, union, -2 to positive infinity. All that cuts out is the -2. Cuts nothing else out. -2.1 that's on the left side of it, still in play. -1.999999, still in play. The -2 is the only spot that's cut out. Okay, so that's how you cut out a number in interval notation. Easy in set notation, you just put not equal to, right? But this is the interval notation for that. It's a little bit more difficult, but if you can understand it, kind of visualize that walking on a number line and hopping over the number and using this to hop over the number. That's how you hop over a number. Okay, we'll see that some more as we go along here. Makes it, maybe it'll make more sense as we do a few more. All right. Example L. Anytime I see that, I got to think, oh, what's up? Red flag. Red flag, red flag. Why is that a red flag? Square root with a variable in it. If it's a square root of a plain number, no problem. The problem is that it's got a variable inside of the square root. What kind of numbers can we take the square root of and it not be weird? Well, a lot of even numbers it's easier to take the square root of, but not necessarily, because I can take the square root of 9 and it's not an even number, right? Does anybody remember imaginary numbers? The I. You've heard that before. Complex numbers, imaginary numbers, you may have heard that word before. Those kind of numbers come from negatives inside of a square root. We can take this. What's the square root of 0? 0, always. The square root of 1, 1. The square root of 4, 2. Square root of 9, 3. Those are positive numbers and 0. If I said the square root of -4, then it gets a little weird. Because if you take the square root of -4, it's a negative under the square root, so there's this imaginary component that comes out with it. It's actually like 2i that the square root of -4 is. So we can't deal with that. Not when we're talking about domain. Domain's talking about the numbers, like the real numbers. an I is not a real number. So when we've got a red flag because of a square root, what we need to know is, when is that greater than or equal to 0? Because we can take the square root of 0, we can take the square root of a positive number. So we're going to take x minus 5 and put it as greater than or equal to 0. So anytime we got a square root with a variable inside of it, we're going to set whatever's inside of the square root greater than or equal to 0 and solve it. That'd be x is greater than or equal to 5. If x is 5 or bigger, then it works. Because if I've got 5 minus 5 is 0, I can take the square root of that. If I had 6 minus 5 is 1, I can take the square root of 1. If I had 7 minus 5 is 2, I can take the square root of 2. It's an ugly decimal, but I can take the square root of it, right? So I get, as long as x does that, I'm good. So the domain in set notation is all the x's that are greater than or equal to 5. It's super easy on that. Now, with the interval notation, this is actually easier on interval notation than the others were, because you're not hopping over a number, you're starting at a number. What number are we starting at? 5, and going up, right? Because it's x is greater than or equal to 5. So we're going to start at 5 and go up toward positive infinity. The difference here is that it's got an equal to mark on it. So we want to count the 5. 5 is in our answers. So the way with interval notation to count something is use a square bracket. The square bracket says 5's included in the answers. Use it and then go to the numbers above it. Okay? The side on the infinity will always be a parenthesis. If you're skipping a number or leaving a number out, it's always a parenthesis. If you've got an equal to mark on your inequality, it always should be a square bracket. Parentheses mean it can't be a bracket on the infinity because you can never really get there. Because once you get there, you just add 1, you're not there anymore. That's the idea. That reason it's always parentheses on the infinities. Brackets can only go on numbers. All right. Let's look at another one. Let's look at there's a couple more here, and then we'll get into a little bit more of this. So what letter are we on? M. Let's say we had f of x is equal to 6 over 2x plus 7. What did I change about how I wrote this problem between example L or example, what is it? Did I skip a letter? I guess I didn't. M. L and M. It's not y equals. I put f of x equals. This is the same thing as y. Those are the same thing. Okay? This is function notation. What that's saying is, hey, this is a function, where the other ones were not necessarily didn't have to be functions. Okay? We know this is a function. Here's the equation for it. We're going to use function notation. And that's just changing y to f of x. It's how they give you the problem. It really doesn't change anything but how it works. If we're going to find the domain of that, what do? Is there a red flag on this one?
Yeah.
Yeah. Got an x in the denominator. That's a problem. How do we take care of it? Say that again, Mom.
What to do? Greater than equal to 0.
That's with the square root.
Oh, that just equal to 0.
Just equal to 0 because it's in the denominator. Anytime it's just a number, a variable expression in the denominator, we're going to go equal to 0. The greater than or equal to 0 comes from square roots. Okay, that's the only time we use square root. The greater than or equal to uses square roots. Okay. All right, let's solve that. What do? Subtract 7. 2x equals negative 7. Last move, divide by 2. We get this fraction, negative 7 over 2. We know that's the thing that x cannot be. So in set notation, that's the easy one. X, as long as X does not equal negative 7 over 2. In interval notation, how do we write that? Remember, we're skipping a number. What goes right here? Parentheses. Another parentheses. Good job. Perfect. Not too hard. Set notation, yeah, it's easier. It's shorter. But interval notation, not that much more difficult once you learn kind of the pattern of way things go. They never change patterns. Okay. Let's look at one more and get the domain, and then we'll move on to something else in this section here. Let's say we had g of x, square root of 3x plus 5, and then a plus 8 on the outside. I put a little tail at the end of my square root so you know the plus 8's on the outside of it. G of x, still the same thing as y. Nothing, it's just different letter. So, what part is the red flag? The square root part. The plus 8 that's hanging out here, is it a problem? No. The only thing that's got a red flag on it is the square root with the x inside of it. So that's the only part we're going to use to set up our problem. 3x plus 5 is what? Greater than or equal to 0. Solve that. 3x greater than or equal to negative 5. Divide by 3. Only thing you've really got to be careful at when you're solving these inequalities is if you multiply or divide by a negative to solve it, what do you have to do to the symbol? Flip it around. That's one of the rules. That if you multiply or divide by a negative to solve it, then you got to flip your inequality symbol. Here, we divided into a negative, but we divided by positive 3, so we don't flip it on that one. All right, so that makes our domain easy on the set notation. X is greater than or equal to negative 5/3. Interval notation for that. It says X's are bigger than or equal to negative 5/3. So what's the smallest number? Negative 5/3 is the smallest number we can use. Bracket or parenthesis? Bracket, because it's equal to, right? And it goes to where? Positive infinity, because it's going up. Right? So it starts at negative 5/3, counting it, and then go up to positive infinity out of that for the domain. Take a little bit of practice, get good hang of the interval notation and the set notation. Make sure you got both of those, but it just takes a little bit of practice on that, and just checking to make sure you did it right on that. All right, let's look at function value. So this is not finding the domain. This is actually taking an x value and finding the y value that goes with it. This is example O, is that right? N was the last one. O. Just like a donut. Kind of hungry. Been a while since lunch. So we got a example O. Let's say it's f of x. So we're using function notation again. So f of x is the same thing as what? Y. Understand, those are the same things. The difference is that f of x is more descriptive. It says it's y for a certain x value. Okay, and that's where this comes in. The function value. Find f of negative 2. Okay, our function is written f of x. So where do you guess the negative 2 goes? Everywhere there's an x, that's where the negative 2 goes. That's what function value is. It says find the y value when x is -2. So it's a very descriptive way of saying y. It says, what's y when x is -2? That's what that says in a really short notation version. So f of -2 means plug in a -2 everywhere there's an x. And work out that side. 3 times -2 is -6, minus 7, -13. So f of -2 is equal to -13. The most common mistake that I see in every, from pre-algebra up through statistics, if you're talking about function notation, is people want to divide by -2 at the end and get f by itself. That's not what you're doing. You're trying to just work out one side. When you're doing function value, you only work out one side of the problem. What it creates is it creates ordered pairs. It creates an ordered pair. An ordered pair. Yes, that's exactly what it's saying. That these two mean the same thing. That this ordered pair, -2 for x, -13 for y, is the same thing as this. But that's specific to this function. That's what that's saying. That's what that creates, is ordered pairs. I think if you understand that, then the temptation to get f by itself goes away. Just understand you're getting an x value and making a y value out of it with some just special notation out of it. It creates this ordered pair. They hardly ever ask you to go back and forth between ordered pair format and function value format. They just expect you to know that it's the same thing. Okay, so know that it is the same thing, and then it makes it easy. It's just like, oh, well, I don't have to do anything else. G of x. Here we go. X squared minus 3x plus 7. So a little bit more difficult function. It's still a function. There are no red flags in this function. If we were asked to do domain, the domain would be -infinity to positive infinity. But here we're asked to find g of -4. What does that mean we do with the -4? Put it in for x. Everywhere you see an x, put a -4. And I am really picky, and I put it in parentheses when I'm showing that I'm doing that, because those parentheses matter. If I'm going to type it into my calculator just like that, I need those parentheses for the same reasons that we talked about in lab. That if I square -4, I mean it for my calculator to do -4 times -4. If I don't put it in parentheses, my calculator will say negative and then 4 squared. And I don't want it to do that. I want it to say -4 times -4. So be careful of that. You can still use that table trick with typing this into y equals, and then use the second graph to go to the table and use that to find function value. I don't usually do that if I'm only asked to find one function value for the problem. If I were asked to take the same function and find several function values, then I use the table. But I normally just do one off, just do one at a time there and work that out. Usually I do it by hand most of the time, but that's me. I'm a math teacher. I'm supposed to do stuff without a calculator, right? I'm not expecting you to. Y'all got a calculator? $100? Use the thing. That's the way I look at it. All right, so 16 and 12 be 28 and 7, 35. So what's the ordered pair that creates? -4, 35. That's the ordered pair. So if you ever got asked, hey, what ordered pair does that function value give you? You know what it is. You know where it came from. Not, it's nothing incredibly fancy. All right, let's look at what if they don't give it to you in equation form. Equation form is the easiest form in this, to me in this, and to most students that I've had. Equation form is easy because then you just plug it in, you work it out. That makes sense. Where people get tripped up a lot in this course is when they throw it at them like this. If you're given f and then a set, -3, 5, 0, 3, 3, 1, 6, negative 1. That's a function in set notation, not equation form. That's weird. But then they ask you to find f of 3. This is where most people get tripped up. But we already know something about f of 3. What does that mean? That x is 3. We're looking for what? We're looking for the y value that goes with 3. What y value goes with 3? 1. There's x being 3. The y value that goes with it is 1. Think. These are ordered pair form. Here's function notation form. 3, 1, 3, 1. Those go together. Okay? If they ask us to find f of 0, it would go with what? 3. Because 0 is the x value. You go up here, you find the ordered pair, it goes with 0, 3. That's the y value. This is the type of problem that seems to trip most people up in this class. May not trip you guys up, but it does. It has in the past. Some of my other students. So I just wanted to make sure I stuck one of those in there so that you could make sure you knew that. All right, let's look at one last thing in this section. I told you this section is the longest one of the night, so we're almost. This is the last thing, and it's example R. I got to write this up here. Increasing, decreasing, and constant intervals. Sorry, intervals. My R's and my B's are starting to look alike tonight. They still do. It's okay. Increasing, decreasing, and constant intervals. And I'm going to draw a graph here. Just get close to what I'm drawing. It doesn't have to be perfect because mine's not going to be perfect. Case in point, my x-axis is not straight. Let's see. Draw. Put a dot there, and then draw a flat piece across. Put a dot there. Put that there. Okay. This ordered pair for this dot right here on the left is -2, 6. This ordered pair for the dot on the right is 7, 6. Okay. All right. What we're looking for here is intervals of increase and decrease. Okay. Now, let me swap that around. Let's change that last picture. I'm sorry, because I just realized I left out something. Same point, just turn it down. It looks like the top of a trapezoid. Make it look like that. Still the same 0.76, but that gets us one of each thing, which is what I want. That way we don't have to do another example. All right. Now, we're looking for intervals where this thing is increasing, where this thing is decreasing, and where it would be constant. Not every graph is going to have one of each of these. It's possible to have none, no increasing intervals or no decreasing intervals or no constant intervals. This one has all three, okay? If something is increasing, you've got to keep in mind as you're looking at this is we're reading a graph, and when we read a graph, we read it like we do a book, left to right, okay? So if we're looking for something that's increasing, when we're reading it left to right, which direction should it be going if it's increasing? Up and to the right. Where is that happening at? Yeah, bottom left. This section right here. That is going up and to the right as we read it. Yeah, the arrow's pointing down. That's okay. That means it's going toward negative infinity there, right? But it's going up and to the right as we read it. Okay? So the interval for increase for here, what's the this arrow going this way? It's pointing down, so in the y direction we're going toward negative infinity on the y's. Well, what direction on the x's is it going? Still going left, isn't it? If it keeps going forever to the left, where's it headed? Negative infinity. Okay, so the increasing interval starts at negative infinity and goes to where? Where does it stop increasing at? At the x value, negative 2. The y value doesn't matter. We use a parenthesis there because we can't say it's at negative 2, put a bracket, because really at that corner, is it increasing or not? You don't, it's hard, you couldn't tell. You'd have to make a guess one way or another, and you'd probably be wrong no matter which way you went. So we're going to use a parenthesis on intervals of increase, decrease, and constant. We use parentheses throughout the whole thing. No brackets ever. Okay? Now, at negative 2, it turns flat. What would that be? Constant. If something is constant, it's steady, right? It's always the same. So it's constant from negative 2 to where? 7. So the interval for constant is from negative 2 to 7. Doesn't matter about the x values. It's y values are what we're looking at. It's x values that we're reporting. Great question, because that is exactly what happens there. Yes, x values are increasing, but that's just location. X values are where, y values are what's going on. Because the y values here, the x values are increasing, but the y values are increasing. That's the part we're wanting to know about. It's what the y values doing here. This leg, the y values are going up. Here, the y values are staying at 6 the whole time. They're staying the same. Y values stay the same. We report the x values, though, in our intervals. Intervals are always of x values. Okay? Now, what happens here at 7?
Decrease.
That's decreasing. It's going down. The y values are going down. The x values are still increasing, but the y values are going down. So that's why that's an interval of decrease, because it's going down and to the right. So it starts at 7 and goes to positive infinity in this case. So we find those intervals of increase, decrease, or constant intervals on that. And that gets us through the first section. All right. Fun stuff. All right. Do we need to break, or can we just push through? Keep going. Get done. I'm with you on that one. That's what I want to do. If you need to run to the restroom or whatever, that's, we're all adults here. We know that stuff happens. You don't need a hall pass. My kids at school. All right. I'm using some graph paper here just so I can be more accurate with my graphs. I'm not necessarily going to say that you have to have graph paper for this. We're doing some basic function graphs, recognizing what they do. Okay, so I'm just using graph paper so I can draw a little bit better, and my OCD tendencies don't start making me go crazy. Okay, so graphs of basic functions, and with this, what I'm after here is for you to recognize the graphs of basic functions. Okay, recognizing an x squared graph, an identity graph, those sort of things. Recognizing what they look like, knowing some basic information about them. Okay. All right. So the first thing that we want to kind of clear up here is this thing called continuity. 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 Continuous functions over an interval can be drawn without picking up your pencil. Okay. What do I mean by that? Continuous functions over an interval. That interval is the domain, by the way. What I mean by that is if you got a coordinate plane here. Whoops. Oh, it's straight there. There you go. You got a coordinate plane. I can draw that entire graph without picking up my pencil. There was no jump. There was no skip. There was no break in the graph. That's a continuous function. Okay. So this one would be an example of continuous. This next one is a good example of discontinuous. Starts the same, but then has a dot on the end and then does this. There's no way that I could trace that and draw it exactly the same way without picking up my finger or picking up my pencil and moving. That would be discontinuous because of that. So this is discontinuous. The last one is the sneaky one. Got a coordinate plane. Got a graph. And they put that in there. Looks a lot like the first one, right? Almost exactly the same, except for one major difference. This thing. That hole in the graph. That empty circle means that you're skipping that. It's like the -2 when we were talking about interval notation. That means that x value doesn't work. And if that x value doesn't work, then that means that y value doesn't exist. Okay? So this one, you really do have to jump over that number. So you have to pick up your pencil to continue the graph. Okay? So this is a discontinuous graph. It's sneaky because they just sneak that little empty circle in there. And it's easy to overlook. Because they may have some dots plotted here that are filled in circles. But here they put an empty circle. That's a discontinuous graph because of that hole in it. That right there makes it discontinuous. All right. Now, let's look at some basic functions and some information about them. Okay? So, basic functions. The first one, we'll call this the identity function. The equation for that is f of x equals x. The domain, negative infinity to positive infinity. The range, the same. I'm going to draw the graph of that beside there. The graph of the identity function is a line. Goes through the origin. The reason it's called the identity function is because no matter what x is, y is the exact same thing. If x is 2, y is 2. If x is -4, y is -4. It's the identity. They match each other. That identity function means it matches one another. It's kind of like the you may not know this, but the additive identity in arithmetic. What number can I add to something and get the same thing back? 0. 0 is the additive identity because 3 plus 3 gets me 3 back. That's why it's called an identity. It gets you the same thing back. This is an identity function because no matter what x is, I get the same number back for y. That's why it's called an identity function. So that kind of helps you remember that name because the name's going to come up. So I want you to kind of tie that together. All right. The next function, number 2, is the squaring function. F of x equals x squared. I'm gonna save myself a little bit of handwriting here. The domain and the range, or the range is a little different, but the domain is the same. Negative infinity to positive infinity. The range is from 0 to infinity with a bracket. And I'm going to draw the graph and show you why that is. The squaring function, it's easy to see where it gets its name because it's x squared. You're squaring x, the squaring function. Yeah. All right. Do very good there. Nice little parabola shape is what that is. So not a sharp V. It's a kind of a soft U at the bottom. But squaring function, the domain, it continues to the left. It continues to the right forever. So that's why it's negative infinity to positive infinity. The range starts at the origin and goes up to positive infinity. So that's why the range is from 0 to infinity there. All right. The squaring function. Continue that trend. We'll go with the cubing function. F of x was x cubed. This one, the domain and the range is exactly the same as the identity function. That's what the graph looks like. It's almost a straight line, but it's bent a little bit there in the middle. It bends. Domain, negative infinity to positive infinity. Range, very obviously, negative infinity to positive infinity. The domain definitely, it's slower about getting out there to negative infinity. It's slower about getting out there to positive infinity, but it's still going out in both directions. It's pretty vertical, but it still kind of just barely veers out in both directions. Okay, so the cubing function, it'll recognize it in its graph. Know that domain and range that go with it. Okay. The fourth one, the square root function. Square root of x, really easy. Okay. Domain, definitely different on this one because we know that what happens when you have the square root with an x in it, there's a restriction on the domain. This one starts at 0, goes to infinity. The range does the exact same thing. Starts at 0, goes to infinity. All the graph there. Starts at 0, goes to infinity. 4, 2. All of that shape. It's kind of like taking the squaring function, the second function we talked about, and turning it on its side and just cutting the bottom half off of it. Like my paper here, There's the squaring function up there. If I turn it on its side, it does that. I don't have an elbow in here. I could show you the little camera thing. But anyway, it just turns it on its side. It's a sideways parabola, but it's only half of it. The square root function. All right. Same idea. Go to 5, and we're going to do the cube root function. F of x is the cube root of x. We don't use this one a ton in 100. It comes up in 110 some, but it's very, very similar to the cube. Its domain and range are still negative infinity to positive infinity, both of them. Okay, the graph of it really does just take the cube root, the cubing function, and lay it on its side. Like takes the cube function and lays it on its side. That's all it does. Real simple. And then the last one is the absolute value function. Absolute value of x is just the straight up and down bars. They're treated like parentheses if you had something to do in order of operations. The domain for this one, the domain is negative infinity to positive infinity because we can take the absolute value of any kind of number there is. Any negative number, we can take the absolute value of it. It comes positive. Any positive number, take the absolute value of it, stays positive, right? The range, because when we take the absolute value of something, the answer is positive, is from 0 to positive infinity. The graph of the absolute value function is a V shape, always. All right. So the V shape, 0, 0 is in there, 1, 1. And for the basic function, just straight shots on each side. That's that V shape. Absolute value graph is going to be that V shape. Got to be able to recognize these, and as we move through the next section, we're going to use them a little bit. Okay, what's it going to do to a graph based on, what we're working with? All right. All right. Got one more section to go, and it talks about graphing techniques. And we're actually not going to draw graphs. We're going to talk about graphs with this, which is weird. But we'll look at them on the calculator a little bit to help us get an idea of what's happening here. All right, so regular notebook paper is what I'm going to be using. Section 2.7 is called Graphing Techniques. Last section of the night, and we'll get out of here. Oops, techniques has a Q, not a G. Graphing techniques. All right. Graphing, excuse me. Graphing techniques. What we have here are things that happen vertically and things that happen horizontally. And where the math happens decides which one it is, vertically or horizontally. So the first thing that we want to talk about is a vertical stretch. Okay. A vertical stretch is going to take an original function and it's going to multiply it by some number on the outside. And if it's a stretch, that number is going to be bigger than 1. Okay? But it's on the outside. The key we've got to get here is vertical things happen on the outside. Vertical things happen on the outside. Say that again. Vertical things happen on the outside. Vertical stretches, shifting something vertically up and down, Vertical compressions all happen on the outside. If that number in front is bigger than 1, it's a vertical stretch. What that means is we're going to take one of these basic functions that we just went through the pictures of, and we're going to take it like, did anybody ever play with silly putty growing up? Where you took it and you pressed it down on the ink of the newspaper and you pulled it off and the picture is on there. I always did the comics, Calvin and Hobbes and or Hobbes. I'm not sure how to say that. Never knew. But anyway, Garfield was a big one at my house. And you'd take a picture of Garfield and be on that silly putty. And if you pulled it this way, it'd make Garfield skinnier and taller. It'd stretch the picture out. That's what a vertical stretch does. So it would take like maybe the absolute value graph. We got a V shape. That's an easy one to do with my hands. And if we did a vertical stretch, if I stretch that up, it's going to make it taller. And when you make something taller, what's it make it look like? Slimmer, right? Y'all ever use Photoshop? That's an awesome thing, man. You can make yourself look really skinny if you want to do that. It takes a lot of stretching for me, but maybe not for some of you guys. But that number on the outside is the key, okay? So an example of that would be like if we have this function 2 and then absolute value of x. Since we talked about absolute value of x, stretching it out makes it taller, makes it look slimmer. That 2 in the front, because it's a bigger number, that's going to be a vertical stretch. This indicates vertical stretch. If I had, we'll call this, what if you had another function? Write it in red. F of x. If you had an x squared function and you put a 4 in the front of it, the squaring function with a 4 in the front of it, that's a bigger number than 1. It's on the outside. You're multiplying by a number on the outside of the x squared. That right there tells you that it's a vertical stretch. And I guess the way of saying that would be, this is a vertical stretch by a factor of 2. This is a vertical stretch by a factor of 4. Okay? To be a vertical stretch, what kind of number has to be out here in the front? Something bigger than 1. To be a vertical stretch, it has to be something bigger than 1 multiplied out on the front. That's what makes a vertical stretch happen. Okay? Now, the next thing is a vertical compression. If you compress something, what happens to it? You squish it down, right? We've all taken a Coca-Cola can and smashed it down, right? Compresses it, makes it shorter, right? And, if you compress down this plastic bottle, it's going to spread out a little bit when you do it, right? So that vertical compression, what it does to the look of things, it's going to make it shorter, but it's going to spread it out some. So if it was the absolute value graph, that V would look wider, but it's really just squishing it down. It's a vertical compression. You might hear me say the word shrink. That means the same thing, okay? Compression is what I try to use the correct word there, but I learned it shrinking when I was in high school, I guess, and it's stuck and I can't get rid of it. The look is exactly the same. You got that parent function or that basic function, absolute value, x squared, cube root of x, that sort of stuff. You got a number multiplied on the front. The difference is that number is between 0 and 1. Small fraction. Decimal. Be a small fraction or a decimal. There. Examples of that. F of x is equal to 1/3 absolute value of x. F of x 0.5 x squared. Those things right there, that right there, and that right there, scream vertical compression. The idea is not for you to actually know, oh, this is a vertical compression by a factor of 1/3, and I know the graph looks like this. We can get the graph. We got a calculator that can graph some stuff. The idea is that you be able to look at an equation and tell what happened to it, to the parent graph. Did it get vertically stretched, compressed? Did it shift left, right, up, or down? That's what we're after here. We're not necessarily after you actually being able to draw the graph just based on the transformations that are happening. We can get the graph with just plugging in X values and getting the Y values, making a table like we did last week or 2 weeks ago. Okay, that's not what we're after. We're after recognizing what's happening. Vertical stretch, vertical compression. Really easy to recognize. Now, here's where we muddy the waters. We got more than two things that can happen. Horizontal stretches. A horizontal stretch happens on the inside. And it works the opposite way. If it's going to be a horizontal stretch, it's going to happen on the inside, and that's going to be a small number. Horizontally stretching is like taking the silly putty with a picture of Calvin on it and going like that. Makes him, widens him out. Looks like it shrinks it down too, but it's really just a horizontal stretch. Widens it out. That's what we're after here. An example of that, kind of using the same idea as what we've been doing. Instead of on the outside, it's a number on the inside. It's 1/2 X, something like that. The horizontal is the opposite way on the numbers. It's a stretch when that's a small number in there. It's a shrink or a compression when it's a big number in there. Okay. Another example of a stretch would be with the x squared function. You might have 0.7 x and then the squared on the outside. It happens on the inside. If it's horizontal, it happens on the inside. If it's vertical, it happens on the outside. Okay, tie those together. That carries over to the next thing that we'll do. Okay, that's a horizontal stretch. Those numbers on the inside. Horizontal stretch. All right. Horizontal compression. All right. Horizontal compression. Still going to happen on the inside. Still A times the X. A is bigger than 1. Okay. A's got to be bigger than 1. Examples of that, using the same ones we've been talking about, the absolute value of like 3x or 5x squared. Those things here and here say horizontal compression. The thing about these transformations that we recognize, they are very difficult to recognize on a graph, but very easy to recognize in an equation. Okay? And the idea is that when we look at an equation, we want to be able to visualize what's happening to it. We know the basic graph of x of the absolute value of x is a v. If we look at one and we see a 3 on the inside times the x, we should know that, oh, that's a horizontal compression, so that's going to make it skinnier. That's what we should be recognizing. If we see a 1/3 on the inside of that, we know it's a horizontal stretch, so it should be making it wider. We should, if we see a number multiplied on the outside, then it's like a 7. We know it's a vertical stretch. That's what I want to. That's what we're after here, is trying to recognize those things. All right. Now, another thing that happens with multiplication, we're getting all the multiplication out of the way. Then we're going to get the addition and subtraction in there. Okay. So the other things that can happen with a multiplication are these things called reflections. There's two different kinds of reflections. One is across the x-axis. It's a negative on the outside in front. It's on the outside. Okay? Here's the thing about reflection across the x-axis. This within my ruler is the x-axis. Okay? If my hand is above it and I reflect across that, what happens to it? Moves down here, right? Does that. What values changed? The y's. The x values stayed the same. The y values changed. Okay? So this is a vertical change happening on the outside. Okay? The negative on the outside. Now, normally you'll see a number with that, like a -2 or something like that, and that's a combination of a reflection and then a stretch together. Okay? If it's just the negative, it's just a reflection across the x-axis. So that's vertically how it reflects. The other way would be across the y-axis. If I'm on the y-axis, my hand's on this side. I reflect across the y-axis. My hand goes over here. What changes? The x values. Where my hand is vertically doesn't change. Where it's at horizontally does. So that's a horizontal. Horizontal things happen where? Inside. So the negative goes on the inside. It's like that. Okay. Recognizing those things. Being able to recognize those. Okay. All right. Let's get into the addition, subtraction stuff, the translations. Translations, if you hear the words translation, you're talking about moving left or right, up or down. If you talk about transformation, that's a combination of it all. That puts it all together. So a translation, left, right, upside, left, right, up or down. Okay. Now, vertical shift. This is the easiest of them. Y equals, you take the original function and add something to it. Okay. What that does is it moves vertically k units. All right. Example of that. F of x equals absolute value of x plus 5. That right there, that part says it moves up 5 units. If you had f of x is equal to x squared minus 3, that part right there says it moves down 3 units. Pluses on the outside are up. Minuses on the outside are down. All of vertical movement because it's happening on the outside. Vertical shifts up and down happen on the outside. Remember, everything vertical that happens on the outside. Everything horizontal happens on the inside. Okay, so a horizontal shift. It's where you take y equals, and on the inside, you're going to add some number. That, if you're adding, if it's a plus sign in here, that's going to move it left k units. If it's a minus sign on the inside, that's going to move it right k units. Okay. It happens the opposite. Normally plussing, moving left to right, plus would move it to the right. It's the opposite. Just like the flip-flop on the horizontal stretch and compression is. It's the opposite thing happening on the inside. So pluses on the inside go left, minuses on the inside go right. All right? let's look at some transformations. And we're going to describe what's happening. All right? And then we'll get into some symmetry test and odd and even test, and then we're done. All right, so describe transformation. Or transformations, I guess would be a better way to say that. We're going to look at more than one. Example A. Here's our function, 3x squared minus 7. Okay? So we're just going to describe what's happening to the x squared, the parent function or the basic function. The basic function is the x squared one in this case. Okay? What does the 3 in the front do? Is it on the inside or the outside? It is? Inside of what? Well, the 3 is what we're looking at. It's touching the x, but it's not in the parentheses with the x. So it's really on the outside. So that's a vertical. This 3 is a vertical stretch by a factor of 3. The minus 7 is on the outside. So it's a shift down 7 units. This one's got a lot more going on, but it's still the idea. You got to look for what's inside. And if it's inside, that means it's going to be inside the parentheses or inside the absolute value marks. So what's the only part that's inside here? The x plus 4. That's the inside. So the plus 4 on the inside tells us to do what? Left 4. What does the plus 13 on the outside do? Up 13. Up 13 units. Left 4 units. What's the 1/2 in the front do? It's on the outside. Vertical compression. By 1/2. A factor of 1/2 really is the word you would say, but a vertical compression by 1/2. Left 4 units because the plus 4 on the inside. Up 13 units because the plus 13 on the outside. Okay. Let's do one more. Absolute value marks. 2/3 on the inside with the x. And then a minus 8 on the outside. We know what any part of that does. The 2/3 is a horizontal what? Yeah, it's a horizontal because on the inside. It's a stretch because it's a small number. And then by 2/3. What's the minus 8 on the outside? Down 8. It's on the outside, so it's going to go up or down. Anytime it's on the outside, it's up or down. Inside, adding, subtracting on the inside is going to be your left and right. Outside is going to be up or down. This just takes practice and following, look at your notes, follow those rules and learn those rules, basically. It just takes practice out of that. All right. We got a couple of tests that we need to talk about, and then And then we'll be out of here. All right, so let's talk about symmetry test first. And then we'll talk about odd and even test and see where they overlap, because they do. Tests for symmetry. All right. There are different symmetries that we're testing for. If we're looking for symmetry, and what is symmetry anyway? What is if something is symmetric? What's that mean about it? Same on both sides. That's exactly right. So there's different symmetries that we're looking for. Test for the symmetry. One of them would be with respect to the y-axis. The test for symmetry with respect to the y-axis is you plug in negative x and simplify. Here's the if then. If everything returns to original, then it is symmetric to the y-axis. Okay? Everything's got to go back to the way it was at the beginning. An example of that. Y equals x squared plus 4. That's our original equation. We want to know if it's symmetric about the y with respect to the y-axis. Plug in negative x and then follow exponent rules or order of operation rules. That's still the same thing. Order of operations rules the game. So when I square negative x, that's negative x times negative x, which would be positive x squared plus 4. Is this line the same as that line? Yes. Then that means that equation is symmetric with respect to the y-axis. Okay? All right, so that's the test for symmetric to the y-axis. Let's get the test for respect to the x-axis. Okay? Symmetric with respect to the x-axis. Okay? Plug in negative y and solve for y again. If everything goes back to original, and guess what? It's symmetric to x-axis. So we're going to use the same example and decide if it's symmetric to the x-axis. Negative y equals x squared plus 4. To get y by itself again, what do I have to do? Maybe that helps. Divide everybody by negative 1. That'd be negative x squared minus 4. Is that the same? No, it's not the same as the original. That's not symmetric about the x-axis. Now, the last one, type of symmetry you could have is respect to the origin. And that would require it to be both x and y axis symmetric. Takes a pretty special equation to be both of those. That doesn't happen a whole lot. Okay, but it's got to be both of those to be symmetric to the origin. Okay. Let's test a couple, and then we'll get to the last test for odd and even. We should see something overlapping here. Test for symmetry. Example E, x equals y squared minus 3. So they're going to throw some weird ones at you here, and we're going to test it for y-axis symmetry, x-axis symmetry, and if we test it for both of those, we should get origin symmetry for free. Because if it's yes on both of these, then it's yes on origin. That's the way that works. Okay? So, to test the y-axis symmetry, what do we plug in? Negative x. And try to simplify it. Well, does it simplify any? There's no exponent to work out here on this one. Does that look like the original?
Yes.
Close, but is it perfectly the same?
No.
No, that guy right there causes a problem. So that's a no on the y-axis symmetry. For the x-axis symmetry, what do you plug in? Negative y. Well, there is an exponent to work out on this one. What's negative y squared? Y squared. Is that exactly the same as the original? Yes. Can I answer the origin one? Is it a yes or no? I said no. All right. That's pretty easy, right? Know those tests. We'll go ahead and we'll skip that last example there. Let's do this last test. I know you ready to go. So am I. I'm not skipping anything that it's just another example of the same thing. Odd and even function test. This is a handy thing. We'll talk about the real test, and then I'll tell you the shortcut to it. Okay. The real test is almost the exact same thing as we did for symmetry across the y-axis. Okay. The difference is we're dealing with functions on this one, and the symmetry doesn't necessarily have to be a function. The difference in odd and even testing is you're dealing with something that is a function. Okay. The odd and even test is to plug in negative x and simplify. That's the test. Same as for y-axis symmetry. The only difference is you're dealing with functions. If f of negative x is the same as the original, there's no change from the original. That's what that notation says. Then it's even. If f of x, or f of negative x, excuse me, is equal to negative f of x, every sign changes. then f of x is odd. It's got to go back to the original to be even. It's got to change everything to be odd. Anything else is neither. Any other case is neither. Okay. Now, let's look at a few examples of this, and we'll get out of here for the night. All right. So, example F. F of x equals 8x to the fourth minus 3x squared. Is that odd, even, or neither? Neither. Where are you from, I guess? Odd, even, or neither. That's our question we're answering. So the actual test is to plug in negative x and simplify it. If I take a negative number to the fourth power, what happens to it? It turns positive. So that turns back into 8x to the fourth. Negative x squared is just x squared. So that's minus 3x squared. Is that the same thing as the original? Yes. That means that this function is even. Here's the shortcut, guys. Look at the exponents on the variables. What kind are they? Even. Every exponent has to be even. If it's not, then the function can't be even. That's the shortcut to it. The real test is plug in negative x. That's the real test. The shortcut is look at the exponents. If they're all even, the function's even. Let's do same game. Is it odd, even, or even? Neither. Neither. It's a weird word. I think it's a word. 6x to the third minus 9x. The real test is still plug in negative x and work it out. If I take negative x and put it to an odd power, it comes back what? It comes back negative. That's what I mean. Negative 1 times negative 1 times negative 1 would be negative 1, right? Negative 2 times negative 2 times negative 2 be negative 8 is what it turns back. And then on the other piece, negative 9 times negative x would be positive 9x. What happened to everything? Change the sign of everybody. So that would be an odd function. Look at the exponents on the variables. What's the exponent on this x right here? 1. It's an odd number, right? All the exponents are odd. It's an odd function. Okay? If all the exponents are even, it's an even function. If all the exponents are odd, it's an odd function. Any other case, it's neither. Like this. Here's a function, 3x squared plus 5x. If I do the real test and plug in a negative x, as a math teacher, I have to show you this, but I want you to learn the shortcut. This is helpful. This one becomes 3x squared. That turns the sign. Did everything change? No, just one of them did. The other one came back to the same. Look at the exponents on the original problem. There's an even one. There's an odd one. They're not the same. That would be an either. Okay? Everything the same, and they're all even, it's an even function. Everything odd exponents, it's an odd function. If you got a mixed barrel of the things, it's a neither. All right? I'm going to put some suggested problems, page 199, 1 through 85. Obviously, just do the odds and check so you can check. 238. Whoops. 238, 1 through 5. This one doesn't have a whole lot of problems in it, so it's kind of limited. Odd, obviously, except for number 8. I just put that in there because there's not another problem like that. And then 253, 1 through 93. Just pick some of those to do. I don't say do all of them. Just do some of them. Okay. Your Canvas quiz for this week should be out there. And then any questions that you got, email me this week. Labs, we'll do labs next week when we come in, and then we'll test after that. Okay. So make sure you got your calculator with you next week. It doesn't have dead batteries, and you're ready to go. All right. You guys have a wonderful week. Be very safe going home. I think it's raining now. The hurricane has started to come in, but it's just rain. I think we're no worries of tornadoes this week. So